right, so section 10.2, we're still going to be working with radicals, but then in this section, we're going to be relating them to rational exponents. So remember back in chapter 7, we were looking at rational expressions, and those were just fractions with variables in them. Rational exponents are just going to be exponents that are fractions. So first thing we're going to do is go from rational exponents to radicals. So we're going to be converting between the two because they are very closely related. And so we'll go in this direction first, and then we'll go in the other direction. All right, so one really important rule, I'm going to put some stars here because you definitely want to write this one down, is that if we have some term to the 1 over n, this is the same thing as the nth root of that term. So all you do, that denominator is our index, and that's how we're going to convert from rational exponents to radicals. So let's go ahead and look at some examples. So we're told to evaluate each exponential. And so when you're told to evaluate, that basically means simplify it down. And we want to figure out what it's going to be equal to. And the way to do that with exponentials is to turn that into a radical, because we know how to simplify down radicals. We saw that last time. So number 1 here, we're given 8 to the 1/3. And so for this one, since we have a 3 in our denominator, this is our index. And so we're taking the third, or the cube root of whatever term we have here, so 8. And now, because we're evaluating, that just converted from exponentials to radicals. That didn't actually evaluate. If we evaluate, we want to take the cube root of 8. And so this is saying what number times itself 3 times gives us 8? Well, 2 times 2 times 2 is 8. So the answer is 2. So that's how we're going to evaluate these. We're going to go to radicals and then reduce from there. Let's try another one, 9 to the 1/2. So again, we want to figure out which root we're taking. So our denominator is a 2, so we're taking the square root. Remember, square root, you don't actually write the 2 out there. If you wanted to, you could, but standard notation, we don't. So I would get in the habit of just not doing that. So we're taking the square root of 9, and what is the square root of 9? Well, 3 times 3 gives us 9, so the square root of 9 is 3. Okay, let's try some that you have to be a little bit more careful with. So number 3 here, we're given negative 81 to the 1/4. Now, there's going to be a difference between this and negative 81 in parentheses to the 1/4. So let's talk about the difference between these two. So in this first one, that negative is out in front, and it's not attached to the 81, but it is attached to the 81 in number 4 because we have those parentheses. So let's look at the difference between these. So I'm actually going to do number 4 first. This means we're taking the 4th root of whatever's down here. So if the negative is with the 81, then that negative is on the inside with the 81 because they're paired together. If there's no parentheses, then that negative stays out in front, and then we take the 4th root of 81. So just remember, if there's no parentheses, it's not joined with the 81. If there are, then they are stuck together and they have to go under that root together. So what is the difference in the solution here? Well, in number 3, we can take the 4th root of 81. A number that multiplies 4 times and gives us 81 is 3. 3 times 3 times 3 times 3 is 81. And then that negative is just going to come along and go out in front of the 3. If we look at number 4, we cannot take the even root of a negative number. Remember, if it's the square root, 4th root, 6th root, we cannot take the even root of a negative number. So this one is not real. Again, we'll see imaginary numbers in 10.7. For now, we're just going to say the answer is not real. Number 5, negative 64 in parentheses to the 1/3. So for this one, first thing you want to think is that negative on the inside or the outside? Well, we're taking the cube root of negative 64, and that negative is stuck with the 64. So we're taking the cube root of negative 64, negative on the inside. Now it's an odd root, so we can take the odd root of a negative. The negative is just going to stay as part of our answer. And so what number times itself 3 times gives us 64? That's going to be 4. And in this case, because we're multiplying to a negative 64, we're going to have negative 4 times negative 4 times negative 4. Does give us a negative, so the answer is negative 4. All right, let's try a few more. This next one, we're given 1/32 in parentheses to the 1/5. So we put this fraction in parentheses because if we just had 1/32 to the 1/5, this 1/5 actually only applies to the 1 in this one. So you want to be careful, again, with fractions if you have parentheses or not. Most of the time you will. Otherwise, it'll be clearly drawn in that 1/5 is right above the 1, not above the whole thing. But again, no parentheses, it wouldn't apply to the entire fraction. So what we're going to do here is we're going to, again, take the 5th root of the number inside those parentheses. So in this case, it's 1/32. And so we saw this rule last time. We haven't formally gone through it yet, but this is another little introduction to it. We can split this up. So we take the 5th root of the 1 on top and the 5th root of the 32 on the bottom. And that way, the 5th root of 1, remember any root of 1 is 1, because 1 times itself 5 times is still 1. And then what is the 5th root of 32? Well, in order to get 32, multiplying a number 5 times, we need to have a 2, because 2 times 2 times 2 times 2 times 2 is 32. Okay, 2 more. Let me see if I can fit this down here. Number 7. We're given 11 to the 1/3. Now for this one, first of all, what root are we taking? We're taking the cube root of 11. And now 11 is prime, so there are no numbers that you can multiply 3 times to get 11. If you went through 2 times 2 times 2, that gives you 8. 3 times 3 times 3 gives you 27, and we just kind of skip over 11. So we cannot get 11 by cubing a number, and so this one actually can't be simplified any further. So we're just going to leave it like this. And then lastly, number 8, we're given negative 4 to the 2/4. Now notice how so far our rule applies to exponents that have a 1 in the numerator. This one is 2/4, but just like a regular fraction, we can simplify this exponent. It's just another fraction, it just happens to be in the exponent. So 2/4 reduces down to 1/2. So this is the same thing as negative 4 to the 1/2. And now if we go ahead and simplify this, put it into radical form, is that negative on the inside or the outside? Well, the negative is not attached to the 4. There's no parentheses, so it's out in front. What root are we taking? We're taking the square root of 4. And remember that negative's out in front, so you don't want to put it on the inside as well. And this negative's out in front, so we'll leave it. And the square root of 4 is 2. So we get negative 2. All right, so that's the case where you have a numerator of 1, but we're going to have the case as well where our numerator is not 1. So let's go ahead and look at that rule. So when the numerator is not 1, then we're going to have this rule here, and there's going to be 2 different ways you can write it, and we're going to use one more than the other. The other is not really going to be used much at all, but it's useful to kind of relate it back to what we were just doing. So if you have some term, say a, to the m over n, so we're still going to have n as our denominator, still our index, then this is the same thing as taking the nth root of a. So just like we did before, last time we had a 1 up top. Now that we have something that's not a 1, that is our exponent. So the way I like to remember this is n is always the index, and that's always the case, even if you have a 1 on top or some other number. M is on the top of the fraction, so it's going to be out on top in our expression over here. So if you can always just remember that denominator is the index, that's a nice way to remember it. And then this m is still an exponent, so it's going to be up top as an exponent. You can also put the exponent, this m, on the inside. So we're still taking the nth root, but you can also have a to the m. This second one here, the one in the middle, is going to be used most often. And this one's not going to be used a whole lot. So I'll show you one example kind of why that is, and then we'll stick to this middle one for the rest of the time. So let's go ahead and look at some examples. And so this first, for these ones we're told to evaluate the exponential again. So same thing as last time, put to radical form and then simplify. If you can, we can't always simplify these. So number 1 here, we're given 25 to the 3/2. So what I'm going to do here is I'm going to show you what it looks like using both of these methods, and how one of them is a lot easier than the other, especially when you don't have a calculator, because we're not supposed to be using calculators in this class. Obviously, I can't be there to watch you to make sure that you don't, but the goal is to kind of get our arithmetic skills down, and really focus on learning these concepts without a calculator. So I'm going to write them. I've written the same problem down twice. And so what we're going to do, this first one, let's go ahead and do this the less common way. So we're going to take the nth root of a to the m. So this is that last one up here. So we're going to take the square root. This 2 is a square root of 25. And that 3 is going to go on the inside here. So that's how you write it that way, which is the less helpful way. To do it the other way, we're going to take the square root of 25 and then cube that. So it's either the cube goes on the outside or it goes on the inside. Now, if we were going to go ahead and simplify this, if we look at this bottom one here, it's actually pretty nice. So if you remember order of operations, we need to do stuff inside the parentheses first. So basically work from the inside out. On the inside here, the square root of 25 is 5. And then I'm going to keep the parentheses even though we don't need them. It's always good to keep them because if this were a negative on the inside, we would definitely want to keep them. So just kind of keep them out of habit. And then 5 cubed, 5 times 5 is 25, times 5 is 125. Now, that's the nice way. So that's the way you kind of want to always do these. If we were to do it the other way, because we want to work from the inside out, we can't take the square root of this 25 first. because it has an exponent. So what we're going to do is we would have to cube 25 first. So 25 cubed, if I were to put that, I just put it into a calculator because it's a really big number. Can't really do it in your head. We get 15,625. And if you were to go ahead and take the square root of this number, you would get 125. So we get the same answer doing it two different ways. But notice the second way, you don't have to work with these really big numbers. You generally get to work with pretty nice numbers that you should know the square root and the cube of. So definitely stick with the middle option here. All right, let's go ahead and try another one then. And we're just going to do these with the nice method. So 27 to the 2/3. So again, figure out what root you're taking and what your exponent's going to be. So our root is the cube root of 27, and then we're going to square that. And then working from the inside out, what is the cube root of 27? Well, 3 times 3 times 3 is 27, so that's a 3 on the inside. We're squaring that. And then 3 squared is 9. These are pretty nice in general. With this next one, you want to be careful with the negatives again. So for this one, we're given negative 16 to the 3/2. That negative is not in parentheses. So just like before, since it's not attached to the 16, it's going to go out in front, and this exponent does not apply to it. So we're going to kind of ignore this negative and think of this next part as just 16 to the 3/2. So we're taking the square root of 16 and then we're cubing it. But remember, this exponent does not apply to the negative. So the only thing I'm going to put in parentheses is that square root of 16, and then we cube it. So again, this negative is going to chill in front. I'm going to put parentheses here. Square root of 16 is 4, and then we're cubing that. Again, the negative is not attached to the 4, so I'll leave it in front. And 4 cubed, 4 times 4 times 4 is 64. So anytime that negative is out in front, it's going to stay out in front by itself the entire time. If you want to just put it there and just kind of cover it up and ignore it, you can do that so you don't try to bring it on the inside. That's another reason why I like to always put the parentheses so that you don't, it kind of shows that the 4 and the negative are separated. Let's see what one of these looks like when the negative is on the inside. So if we take a look at negative 64 in parentheses to the 2/3, this means that we are doing, we're applying this exponent to negative 64. So this whole thing is going to go on the inside of the radical. We're taking the cube root of negative 64, and then we want to square that. So now, looking on the inside, the cube root of a negative, we can do that because it's an odd root. So what number times itself 3 times gives us negative 64? That'll be a negative 4. So this is one reason why I always keep the parentheses, because putting the parentheses around this negative 4, it's going to give us a different answer than if we hadn't. So you want to keep those parentheses so you get the correct answer. And so negative 4 squared, negative 4 times negative 4 is 16, positive 16. All right, let's go ahead and try just 2 more of these. Number 5, we're given negative 36 to the 3/2. So we just did one just like this, so I would go ahead and try this one by yourselves. So we're going to go ahead and take the square root of, so this negative is paired with the 36, so it goes on the inside, and then we cube that. Now, you should notice something kind of wrong with this one, because we're trying to take the square root of a negative. We cannot do that even if you have other stuff going on outside. Because we're trying to take the square root of a negative, this is not real. The only reason why we were able to do it last time was because we had a cube root, not a square root. This time we have a square root, so it's not possible, so it's not real. And then our last one here, we're given 8 to the 5/9. And you will see a problem like this, and it's going to tell you to use the definition that takes the root first. Oops, combining words. Because for this one, we can only put this into radical form. We won't be able to simplify. You'll see why when we put it into radical form. They want you to use the definition that takes the root first. That's just the definition we've been using, because when we've been going through and simplifying, you take the root first, then you raise it to the exponent. In the other definition, you raise it to an exponent first, and then you take the root. So this is our normal definition. So this is the definition we've been using. And so let's go ahead and put this into the form that we've already been using. So we're taking the 9th root of 8 and then raising this whole thing to the 5th. So we can't take the 9th root of 8. There's no number, no whole number that multiplies by itself 9 times to give us 8. And so this is actually as far as we can go. This has been put into radical form, and that's all we can do because we can't simplify from there. All right, now let's go ahead and look at some similar problems, but this time we're going to use one of our exponent rules that we worked with back in chapter 5 in Math 95. So this old exponent rule is a to the negative n. So if you remember, if you have a negative exponent, we want to make it positive. We're going to move that to the bottom of its own fraction, and it becomes 1 over a to the positive n. So let's go ahead and look at some examples where we use that negative exponent rule with these rational exponents. So we're told to evaluate each exponential. And so looking at this first one, we're given 5 to the negative 2/3. Now, first thing you want to do here is get rid of the negative exponent first. Before you put it into radical form, you have to get rid of the negative exponent. So in order to do that, we're going to move this whole term to the bottom of its own fraction and make the exponent positive. You're not going to flip your fraction in the exponent. You don't touch this term besides changing the sign of the exponent. So this becomes 1 over 5 to the positive 2/3. That's all we did was move it down, make the exponent positive. Now we can put this into radical form. So we're going to leave that 1 on the top. Now, what root are we taking? We're taking the cube root of 5, and then we're going to square that. So make sure you're only squaring what's on the bottom, just the thing that was raised to the exponent. This is all we're doing for this one because you can't take the cube root of 5. Now, if we take a look at another one, this one we're given 4k in parentheses to the 3/5. Now with this one, again, we're raising 4k and it's in parentheses, so they're kind of joined together. They should stay together the whole time, to the 3/5. And we want to go ahead and I completely skipped over a section. Sorry, let me go ahead and erase this one. That's our next section of examples. Let's go ahead and do 32. Nope, 4/9 to the negative 5/2. Okay, there we go. So for this one, we want to go ahead and, again, first get rid of that negative exponent. This one is going to look super weird because this 4/9 is going to be on the bottom of a fraction. So we're going to have a fraction within a fraction, but we want to have that 4/9 on the bottom raised to the positive 5/2. And now let's go ahead and put this into radical form. So we're going to have 1 over. Now we're taking the square root of 4/9, and then we're raising that to the 5th. And this one we can actually simplify because we know what the square root of 4/9 is. Remember, if we're looking at the square root of 4/9, and if you want to do this off to the side, you can, where we can take the square root of 4 on the top, the square root of 9 on the bottom. The square root of 4 is 2, square root of 9 is 3. So this is just 2/3. But remember, we still have that to the 5th power on the bottom. So 2/3 to the 5th power, we're going to raise both of these to the 5th power. So we're going to have 2/3 to the 5th. This is one of our exponent rules. You can kind of distribute that 5 in. So you have 2 to the 5th over 3 to the 5th. And I'm not actually going to write out the multiplication here, but if you were to multiply 2 times itself 5 times, you get 32. And 3 times itself 5 times, you get 243. So I'm going to bring this back over here, and I'm going to put parentheses around that fraction, just so you know that it's on the bottom of the fraction. And now remember, this fractions are the same thing as division. So this is the same thing as 1 divided by 32 over 243. And division, we can, with fractions, we're going to change this to 1 times 243 over 32. Well, any number times 1 is just itself. So this is the same thing as 243 over 32. And this one is about as ugly as these are going to get, especially when you have fractions within fractions. Normally they'll be a little bit nicer, but you will see one like this on your homework. Okay, let's go ahead and take a look at our next set of examples. These are just a separate set of examples because they have slightly different directions. So for these, this kind of combines everything we've seen so far. We're told to write as radicals. Now for these, we may or may not be able to simplify, but we just know that we have to write it as a radical. And you do want to simplify when possible. So this first one here, we're given 4k to the 2/3, and I'm going to leave the parentheses off. Oh, that's supposed to be 3/5. Sorry, 4k to the 3/5. So for this one, you want to be careful. Notice how there are no parentheses around the 4 and the k. You can kind of think of this like when you have a negative out in front and there's no x, or there's no parentheses there. These are kind of separate. Same thing with this 4 and the k. Because there are no parentheses, the 4 and the k are not stuck together. So this k to the 3/5 is its own thing. So I'm going to leave that 4 out in front, and then we're going to apply this exponent just to the k. So we're taking the 5th root of k and then raising just that part of the term to the 3rd power. This is all we can do. We can't take the 5th root of k, so we're going to go ahead and leave it just like this. Some of these answers will just look ugly, but they are correct. Number 2, we're given 5x to the 3/5 minus 2x in parentheses to the 3/5. And I'm going to change that to the 3/4. Yeah, there we go. Okay, so again, first thing we want to do is write these as radicals. So we have 2 different parts here, and we're going to treat them as their own terms because they are. In this first one, just like we saw up above, the 5 and the x, there are no parentheses, so those are separate parts. So the exponent only gets applied to the x. So we're going to leave the 5 in the front. Now we're taking the 5th root of x to the 3rd. So we'll put that whole thing, raise the whole term to the 3rd power, except for the 5, because that's out in front, minus, now with this one, notice how the 2x is in parentheses. So we're going to apply this exponent to the entire term. So we'll be taking the 4th root of 2x and then raising that whole thing to the 3rd power. Now, we were only writing these as radicals, and if we take a look at these, we can't take the 5th root of x, we can't take the 4th root of 2 or x, and so this is as far as we can go. Again, it's a little ugly, but our goal was just to write these as radicals. Let's take a look at one more. This one we're given m cubed plus n cubed in parentheses raised to the 1/3. Now, if you notice with this one has some addition here, but m cubed plus n cubed are inside parentheses being raised to an exponent. So because they're in parentheses, this exponent applies to this entire sum. So what we're going to do is we're going to take the cube root of everything inside the parentheses. So that means m cubed plus n cubed. Now, one thing that you are probably going to be tempted to do, but you cannot, is cancel out the cube root and the cube, kind of like what we did when we took the square root of a squared. This became a because those canceled, but that was a single term. If you have addition here, you cannot cancel those out. Think back to rational expressions where we had something like m plus n over, say, n plus 4. Because these n's were parts of terms that had addition in them, you could not cancel anything out. Same thing here, the m cubed and the n cubed, that's kind of stuck together because of that addition there. So you cannot cancel the cube root and the cubes out. So this is as far as we can go. All right, so we've taken a look at how to go from exponents to radical form. Now we're going to go from radicals to exponentials. All right, so we're going to just go ahead and look at some examples, because this is our kind of the same rules as what we've already seen, and I'll show those again in a second. We're told to write as an exponential and simplify if possible. Okay, so if we take a look back at one of our first pages here, we'll take a look at this one. So the index is always your denominator, and the exponent on your term is the numerator. So just remember index, denominator, exponent, numerator. So let's go back to our examples here. We're given the square root of 37. So this isn't something we can just reduce down because we can't take the square root of 37, but we can go ahead and do what they're telling us to do here. That's write it as an exponential and then simplify, and that's only if possible. So the square root of 37, we don't see an exponent right now, and if you don't see an exponent, that means it's a 1. So our numerator is going to be a 1, and our denominator, we're taking the square root, so our denominator is 2. So we have 37 to the 1/2. And if you want to write the 2 in there, you can. That's as far as we can go. 1/2 can't be reduced, and we can't take the square root of 37. So that one's pretty fast. Let's go ahead and see one that we can simplify. The square root of 2 to the 8th. Now again, our base here is going to be 2. Our numerator is the exponent we see, which is 8. over the denominator, and again, it's a square root, so it's a 2. Now we can simplify this one. 8 over 2 is the same thing as 4. So we can actually write this as 2 to the 4th. And 2 to the 4th, 2 times 2 times 2 times 2 is 16. So we took something, square root of 2 to the 8th, and we wrote it as 16. So it simplifies it down. For this one, we just couldn't simplify it in number 1. Let's go ahead and try a couple more of these. How should we do this over here? So next one, we're given the 4th root of 9 to the 8th. So again, our base is this number on the inside, so it's 9. We are taking the 4th root, so that's our denominator, and our exponent is 8, so that's on the top. Now we can reduce 8 over 4. 8 divided by 4 is 2, so this is the same thing as 9 squared, and 9 times 9 is 81. And then lastly, the 4th root of t to the 4th. We've seen one kind of like this, where we saw the square root of a squared, and those canceled out. It's the same kind of thing here. We could go ahead and just cancel out the 4th root and the t, or the 4th exponent on the t. But what I'm going to do is go ahead and do the steps that they want us to take. So we're first going to write this as an exponential. So we have t as our base. The exponent is 4, so that's our numerator, and our denominator is also a 4. 4 over 4 is 1, and t to the 1st is just t. So you get the same thing. This is just kind of why that works, why you're able to cancel these out. All right, so the last part of this section, we're going to be going in both directions. So we'll go from some rational exponents to radicals, and then we'll do some radicals back to exponentials. But before we get to that, we do need to do a quick review of the exponent rules, because I'm sure it's been a while since you've seen these. All right, so if we have a to the m times a to the n, so if we're multiplying two terms with the same base, they have to have the same base, we're going to add the exponents, so it becomes a to the m plus n. If we have, I'm actually going to do the rest of these in red. Okay, I changed that to red so that these are easier to see. The next one, if we have a to the m, so we're raising an exponent to another exponent, we're going to multiply them. So a to the m times n. The way I remember that is the parentheses that are separating them. We usually use parentheses for multiplication. So we're going to multiply those exponents. Our next rule, a to the m over a to the n. So division, which is the opposite of multiplication. We're going to do the opposite with the exponents. We're going to subtract. So we're going to do always the top minus the bottom. Now, if we have a product, so a times b to the m power, we can distribute that exponent in. So it'll be a to the m, b to the m. Even if you have a number in the front, the coefficient also needs that exponent. And then a couple more rules. If we have a two terms that are being divided, so a quotient raised to an exponent, we can also distribute that this way. So we get a to the m over b to the m. And now for ones that we've already seen, we just saw this one, a to the negative m. This is going to become 1 over a to the m, so make it positive. And same thing if you have the negative on the bottom, so 1 over a to the negative m, then we're going to move it up top and it becomes a to the positive m over 1 or whatever's left down there. All right, so now we're going to use the exponent rules with rational exponents. And so using these exponent rules with rational exponents, so when you have fractions as your exponents, it's the exact same thing, but we're going to be using fractions instead of whole numbers. So it's going to look more complicated, but they're exactly the same rules. So let's go ahead and just jump into some examples here. So we're told to simplify. Our goal is to take the multiple terms we're going to have and combine it into one. So number one here, we're given 11 to the 3/4 times 11 to the 5/4. Now, one thing to notice here is that we have the same base, which means we can combine them. If this were an 11 and a 10 or something that wasn't the same, we cannot combine them, and this would be as far as we can go. Okay, we do have the same base though, so we can go ahead and combine these, and we're going to use our exponent rules. We don't want to change to a radical first. That'll actually make this harder. Let's go ahead and combine these two terms together. So because we're multiplying the terms, we're going to add the exponents. So I'm just going to add them just right below here. So 3/4 plus 5/4. We have a common denominator, so that's nice. We get 8/4, and 8/4 is the same thing as 2. So we're going to keep the base, write our new exponent, and now 11 squared, we know what that is. 11 times 11 is 121. So combine them using your exponent rules and then simplify if you can. Can't always do that, but we could in this one. Okay, let's try another one. This one we're given 7 to the 3/4 over 7 to the 7/4. So for this one, again, you will first want to identify that we have the same base. We do. And you want to make sure that you know which rule you have to use. So because we're dividing, we're going to subtract the exponents. So we're going to have the one on top, so 3/4 minus 7/4. Now, again, we're given a common denominator, which is nice. So 3 minus 7 is -4/4. And -4 divided by 4 is -1. So now keep the base, write our new exponent. And we don't like negative exponents. So you always want to make sure you're getting rid of those. And we're going to do that by moving it down to the bottom of its own fraction. So this is going to become 1 over 7 to the positive first. And 7 to the first is just 7. So this is 1/7. Okay, let's try a couple more of these. Number 3, we're given 2 to the -1/2 times 2 to the 3/4. So again, let's identify first if we have the same base. We do. So we can combine it using our product rule, which tells us that we need to add our exponents together. So we're going to have -1/2 plus 3/4. Now we do need to get a common denominator here. Our common denominator is going to be 4. So our first fraction multiplied by 2, we get -2/4. That 3/4 stays the same. And then -2 plus 3 is 1/4. Now, we can't actually simplify this down. So we're going to go ahead and leave this as 1/4. So we're going to keep our base and then raise that to the 1/4 power. Now, we're not going to change this to radicals because they didn't ask us to change it to radicals. They just wanted us to simplify this down. So we're going to go ahead and leave this as 2 to the 1/4. If they ask you to write it as a radical, you want to make sure that you do that but for this one, they didn't ask us to, so we're gonna go ahead and just leave it. All right, number 4, this one, they're gonna start to get quite a bit more complicated. So this one, we're given 9 to the 2/3, in parentheses, x to the 1/3 raised to the 4th, all over 9 to the negative 1/3. Now, if you remember, first thing you want to do here is get rid of parentheses. So we have this term right here where you have 1/3 raised to the 4th. So this is our exponent rule right here. So we're going to have an exponent raised to another exponent. So we multiply those. Whoops. So we're going to multiply 1/3 times 4 over 1, which just gives us 4/3. So I'm going to go ahead and rewrite that, and I'll keep the rest the same for right now. So we have 9 to the 2/3, x to the 4/3, all over 9 to the negative 1/3. Now, if you notice, you want to see what else you can simplify down. There are no other x's, so I can't actually do anything with this x to the 4/3. So I'm going to keep that there. But I can do something with these 9s. So because we're dividing, I'm going to go ahead and subtract those two exponents. Remember to do top minus the bottom. So 2/3 minus negative 1/3. So now we're going to add the opposite, and we have 2/3 plus 1/3, which is 3/3, which is the same thing as 1. So this is the part that's a little weird. That is our new exponent on the 9, and that is always going to end up on top of the fraction. It's not in the denominator because it's always the top minus the bottom. So that is just a 9 to the 1st, and then x to the 4/3. And now our denominator is gone because we combined it with the 9 on the top. So I'm just going to make this look a little bit nicer. 9 to the 1st is just 9, x to the 4/3. So combine terms with the same base. If they don't have the same base, we can't do anything. Couple more of these. This next one, we're given a cubed b to the negative 4th over a to the negative 2nd b to the 1/5. This entire fraction is being raised to the negative 1/2. Now, this one looks even more complicated. We have more exponents. We have this exponent out here applying to this entire fraction. So first thing you want to do is take care of those parentheses. So we're going to distribute this exponent to everything on the inside. And because we're raising exponents to another exponent, what are we going to do with them? We're going to multiply. So we have a to the 3rd raised to the negative 1/2. So we're going to have 3 over 1 times negative 1/2. That's going to give us a negative 3 over 2. So now we have a to the negative 3 over 2. Now let's look at our second exponent on the b. We're going to have negative 4 over 1 times negative 1/2. Negative times the negative is a positive 4 over 2. 4 over 2 is the same thing as 2. So we're going to have b squared on the top. Now on the bottom, we're going to have a to the negative 2. So negative 2 over 1 times negative 1 over 2. We're just multiplying all these exponents. Negative times a negative is a positive again. So we get 2 over 2, which is 1. So we're going to have a to the 1st. And then lastly, we're going to have a 1/5 on that last b times negative 1 over 2. So we get negative 1 over 10. So b to the negative 1/10. That's kind of the one ugly one there. All right, that is the first step. That is probably the hardest step for that one. You just have to know to multiply every single exponent by the exponent. And that was because the entire fraction was in parentheses, you will see an example where just the numerator is being raised to an exponent. So if the parentheses are only around the top, that is the only thing that will be raised to the exponent. So you would leave the denominator alone. So just a heads up for that. All right, now that our exponent on the outside is gone, we can go ahead and combine our what I call like parts. So we'll combine the A's and we'll combine the B's. And because we're dividing, what are we going to do with the exponents? We're going to go ahead and subtract. So let me actually, we'll combine those, and we'll do that right over here. So remember, top minus bottom, so negative 3 over 2 minus 1 over 1. So let's get a common denominator. We'll make it a 2. So negative 3 over 2 minus 2 over 2. Negative 3 minus 2 is negative 5 over 2. That's all we can do there. So that's our A's. So we're going to have A to the negative 5 over 2. And that's up on top. Our denominator for the A's is gone. And now for the B's, we're going to have 2 over 1 minus negative 1/10. So again, be careful with your negatives there. So we're subtracting a negative, so I'm going to make that a plus. Now let's get a common denominator of 10. So 2 times 10 is 20. So 20 tenths plus 1/10 is 21 tenths. And if we bring this back over here, we're going to have B to the 21 tenths. And now there's one last step because we don't like negative exponents. This A is actually going to move back to the bottom of the fraction. So the B to the 21 tenths is on top, and the A to the positive 5 over 2 is on the bottom. All right, so those get tricky, but that one is about as tough as it gets. The next one looks kind of weird at first, but we'll work through it. So let's go ahead and look at the last one for this section of examples. Then there's just a couple more things to cover. This is a long section, so I apologize. All right, this next one we're given A to the 2/3 times, in parentheses, A to the 7/3 plus A to the 1/3. Now, think about regular distribution. So let's say we have 2x times, let's say, x squared plus 4x cubed. So normally when we distribute, we are multiplying each of these terms. So we're doing 2x times x squared plus 2x times 4x cubed. So distributing, we distribute that term into both of them, and then we're multiplying the terms. So when we multiply these terms together, we add our exponents. We would get 2x cubed plus 2 times 4 is 8. X to the first times x cubed is x to the fourth. We are now going to do the exact same thing over here with our rational exponents. So first thing I'm going to do is I'm actually going to write that kind of middle step. We're going to have A to the 2/3 times A to the 7/3 plus A to the 2/3 times A to the 1/3. So we've distributed that. Now we want to add our exponents because we're multiplying. So we're going to have 2/3 plus 7/3, and that's actually pretty nice. There's already a common denominator. So we get 9/3, which is the same thing as 3. So we have A to the 3rd plus, now if we add our exponents over here, we have 2/3 plus 1/3. Again, we already have a common denominator. We get 3/3, which is the same thing as 1. So we just get A to the first, which is the same thing as A cubed plus A. Starts off messy, ends up pretty nice. So the big thing is there, remembering to add your exponents. A lot of the times I see people trying to multiply them. But just remember, multiplying terms means you add exponents. All right, now 2 more problems. This is a slightly different set of examples. So what we're told to do here is we're actually going the other way. We want to write as an exponential. So we're going to start with a radical, then simplify. So we saw some kind of like this. Where was it? Right here. So these ones were kind of the nicer ones where we wrote it as an exponential and then they reduced down pretty nicely. These ones are a little trickier because we have variables. So first one, we're given the square root of x to the 5th over the cube root of x to the 5th. So now, first thing we want to do here is write these as exponentials. And so we have 2 different terms. We're going to do it to the top and the bottom. So remember the index in this case is a 2. That's our denominator. So we're going to have x to the 5 over 2. On the bottom, we're going to have x to the 5 over 3. 3 is our index, 5 is our exponent. Now this looks just like one of the ones we were just looking at. We can use our exponential rules. We can go ahead and, since we're dividing, we'll subtract our exponents. So we're going to have, I'll do this over here. 5 over 2 minus 5 over 3. We want a common denominator of 6. So the first one has to be multiplied by 3, so we get 15/6. This 3 needs to be multiplied by 2, so 5 times 2 is 10. And if we subtract those, 15 minus 10 is 5 over 6. Now, that is our new exponent, so we're going to have x to the 5 over 6. And that is as far as we can go. These ones kind of simplify down like we did up here. Might be kind of ugly, you'll still have a variable. There's nothing else we can do to simplify it. Now, this next one is where it looks really weird. So we have the square root of the cube root of x. So now what I'm going to do is I'm going to start from the inside out. And so first thing I'm going to do is I'm going to write that cube root of x as an exponential. So I'm going to keep that square root. And now we're going to have x. So if we just had the cube root of x, this is going to be x to the 1/3. So we're going to put that on the inside. And now we have the square root of that. So we're going to take whatever's on the inside, in this case, x to the 1/3. I'm going to put it in parentheses. And now because we're taking the square root, we're going to have this raised to the 1/2. All right, now with our exponent rules, remember if you have an exponent raised to another exponent, you're going to have 1/3 times 1/2, which is 1 over 6. So we get x to the 1/6. So the key for these, that is just getting messier and messier. So the key for these is writing your exponents. So the cube root is the 1/3, the square root is the 1/2. Whichever one's on the outside here, the outside radical is the outside exponent. The inside radical is the inside exponent. So that's the way to remember that one. Or you can go through this process where you start from the inside and work your way out. All right, so that's 10.2. That one is, I think, the longest section in chapter 10, just because there's so much going on. The next section, we're going to be looking at simplifying radicals using the product and quotient rule that we've already seen a little bit. So that's 10.3, and then we're going to continue working with radicals all throughout chapter 10.